Let's look at some examples of one-sided limits. Let's consider the limit of f of x as x approaches 0 from the right. So as x approaches 0 from the right, we're talking about just to the right of 0 on the x-axis. So follow along the function as x approaches 0 from the right. The function is getting closer and closer to height 1 as x approaches 0 from the right. Therefore, the right-hand limit of f as x approaches 0 equals 1. Now consider the left-hand limit as x approaches 0. This function is not even defined for x less than 0, so therefore the left-hand limit of f as x approaches 0 does not exist. Now consider the two-sided limit of f of x as x approaches 0. Since the left-hand and right-hand limits do not both exist, then the two-sided limit of f does not exist either. Now let's consider the behavior of f as x approaches 1. As x approaches 1 from the left, we would look at the graph of the function for values of x slightly to the left of 1. So we're talking about values along the x-axis here, slightly to the left of 1. As you trace the function as x to the left of 1, the values of the function get closer and closer to height 0. Remember that the f of x values, the function's values, are the y-coordinates of points on the graph. So the y-coordinates are getting closer and closer to height 0 at the x-axis as x approaches 1 from the left. So the left-hand limit of f of x as x approaches 1 is 0. But if we consider the limit as x approaches 1 from the right, as we trace the function to the right of 1, the function is staying at constant at height 1. So the limit of f of x as x approaches 1 from the right is plus 1. The height of the y-coordinates are all at height 1, slightly to the right of 1. Now let's consider the limit of f of x as x approaches 1. So in order for this limit to exist, the left-hand limits and the right-hand limits must both exist and both be equal. Well, since the left-hand limit is 0 and the right-hand limit is plus 1, the limit at 1, we would say, does not exist. Now let's consider the behavior of the graph at x equals 2. As x approaches 2 from the left, the function is approaching height positive 1. So the left-hand limit at 2 is 1. If I approach 2 from the right, the function is still getting closer and closer to height 1 from the right. So the right-hand limit is 1. So since the left-hand limit and the right-hand limit both equal 1, then we would say the limit of f of x as x approaches 2 would also equal 1. Now this graph is interesting to note. The function has a little hole at x equals 2, and there's a little dot up high for the point when x is 2. So if we look at the function's value at 2, f of 2 would be the height of this point, so that would be 2. So the function's value at 2 does not affect the limit of the function as x approaches 2. Again, it's important to understand with limits, you're not interested in what happens at the point, but what's happening as x approaches that point. Consider the graph of this function. Let's call this function g. The limit of g of x as x approaches 2 from the left would be found by looking at the graph of the function slightly to the left of 2. Whereas you follow the function along to the left of 2, we see that the function's y-coordinates are getting closer and closer to height 3. So the left-hand limit as x approaches 2 is 3. To find the right-hand limit of g as x approaches 2, you would follow along the curve, but slightly to the right of 2. And we see that as x gets closer and closer to 2 from the right, the height of the graph is getting closer and closer to height 1. So the right-hand limit of g of x as x approaches 2 is plus 1. Since the left-hand limit and the right-hand limits do not agree, they're not the same, the limit as x approaches 2 of g of x does not exist. Let's look at a one-sided limit using algebra. So consider the function g of x, which is defined as x squared plus x minus 6 divided by the absolute value of x minus 2. Now the numerator can be factored as x plus 3 times x minus 2. So I can't cancel the x minus 2's here because it's not the same exact quantity. I have an absolute value of x minus 2 in the denominator. So let's look at the behavior of this function as x approaches 2. We see that this function is not defined at x equals 2 because we would be dividing by 0. We can still evaluate left and right hand limits at 2. So consider the right hand limit of g of x as x approaches 2. So in order to evaluate this limit using algebra, we need to know that we're only looking at values of x slightly to the right of 2. So if you look at the quantity absolute value of x minus 2 in the denominator, if x is slightly bigger than 2, then x minus 2 will be a positive quantity, and therefore the absolute value of x minus 2 would just equal x minus 2. So I'm going to replace absolute value of x minus 2 with the quantity x minus 2, because when x is slightly bigger than 2, x minus 2 is positive, and so I can just drop the absolute value signs. Now we can cancel a common factor of x minus 2 in the numerator and denominator, and this limit simplifies to the limit as x approaches 2 from the right of x plus 3. Since one-sided limits behave the same way as two-sided limits, we can still use direct substitution here to evaluate this limit. So if I plug in 2 for x, I get 2 plus 3, which simplifies to 5. Now let's consider the left-hand limit of g of x as x approaches 2. We're only going to be considering values of x that are slightly less than 2. So think about numbers like 1.9, 1.9999. When x is very, very close to 2, but slightly to the left of 2, then the quantity x minus 2 will be negative. Consider like 1.9 minus 2. 1.9 minus 2 would be negative. So the absolute value of x minus 2, since x minus 2 is negative, when I take its absolute value, I'll have to take the opposite of that number. So in the expression for g of x, I'm going to leave the numerator factored as x plus 3 times x minus 2. But now, instead of absolute value of x minus 2, we said that x minus 2 is negative, so the absolute value of x minus 2 can be written as the negative or opposite of the quantity x minus 2. So when x is slightly less than 2, x minus 2 is negative, so I take the opposite or the negative of the quantity x minus 2. So now when I cancel a common factor of x minus 2, I'm left with a factor of negative 1 in the denominator. And so I get the limit as x approaches 2 from the left of x plus 3 divided by negative 1. Now when I use direct substitution, I get 2 plus 3 over negative 1, which reduces to negative 5. So the right-hand limit as x approaches 2 is 5. The left-hand limit as x approaches 2 is negative 5.